Good morning and welcome. I welcome you all to today's webinar. And in fact, as we've already discussed, sent notices and information across, this is a webinar that we've always been looking out for, because it's something that has been heavily shared and advertised in conjunction with our partners. And we are going to go through it just as we start. So before that, I would like to give a background of what brought up all these, these great events that we have. Okay, so the background of it is that on the 6th of February 2013, a magnitude 7.8 earthquake occurred in southern Turkey near the northern border of Syria, which recorded over 50,000 deaths, including our own brother Christian Achu. May his soul and all the departed rest in perfect peace. So that actually brought grief, I believe, largely to those in Turkey and Syria, and then no country, most countries were not spared at all. This event is proudly brought to you with partnership from Prota Software from Turkey, Cab Royal Limited, Ghana Institution of Engineering, Institution of Engineering and Technology, Ghana. Okay, these two are, of the main professional bodies in Ghana, of which, if you are practicing, you have to be among these two, or else you can't operate or practice in Ghana. So they are, they are our key partners to this event, and they are one of our partners that we really cherish. They've been supportive to us. Even up to this day, and they always open their arms and their doors each time we call on them. GHIE, IET Ghana, we are grateful for your partnership, and we really love and appreciate you. We also have Cap Solutions LLC, which almost sounds like Cab Royal, but that is an online-based institution from Wyoming. It's a US-based registered company that does online training for professionals in the AEC industry. Most of the items in there are run also alongside by Cab Royal. They stream Cab Royal's training online for us. So as I said, we are much grateful for our partners. We are gathered here today because of the importance of being prepared for disasters such as earthquake. It is essential that we as professionals take our role seriously in ensuring that our buildings are structurally sound and can withstand natural disasters. This is especially important given the recent events in Ghana, where we have recently, in fact in this month, recorded 3 building collapses in 1 month without even a tremor. Our esteemed speakers today are experts in their fields and have worked on several projects that demonstrate their experience and knowledge. We have with us Mustafa Tan, who holds a master's degree in earthquake engineering and has over 15 years of experience in structural engineering. We also have with us engineer Kwabena Bempong, who is the president of Ghana Institution of Engineering and the CEO of Associated Consultants Limited, a highly experienced and knowledgeable highway and structural engineer with over 30 years of experience. Our third speaker is also Engineer Henry Kojo Boatin, who is also the current president of Institution of Engineering and Technology, Ghana, and also serves on several committees at government and other built environment agencies. He has worked on several large construction projects from conception through post-tender activities and has a wealth of experience to share with us today. Ladies and gentlemen, I'm confident that after today's event, we will have a deeper understanding of the importance of earthquake resistance building and the need for proper preparation in case of disaster. So let us welcome our speakers and have a productive and informative session. I'm so much honored today to welcome or to introduce our first speaker. His name is Mustafa Tan. We have him as an incredible guest, okay, who is at the forefront of structural engineering, of the structural engineering industry. Mustafa Tan is a true expert in earthquake engineering and holds a master's degree from the prestigious Middle East Technical University with over 15 years of experience as a practicing engineer. Mustafa has been involved in numerous structural engineering projects, including base isolation buildings, seismic performance assessment, retrofitting, and earthquake resistant design. Not in anywhere, but largely in Turkey, which is an earthquake prone zone. So you can imagine his worth of experience. But not all. Mustafa is also the head of the development team of Prota structure, where he applies his extensive knowledge and passion for creating state-of-the-art structural engineering software. His innovative approach to structural and software engineering design is truly inspiring. And I can't wait for him to share his insights with us today. Please join me in welcoming Mustafa Tan to the show today, to the webinar, to take the stage and then share with us as our first main speaker and our guest speaker today. Mustafa, you are welcome. You may take the the stage now. Thank you.
Abel, thank you so much. Hello, everybody. I'd like to start by thanking you all. It's a pleasure for me to speak to such a distinguished audience today. I am Mustafa Tan, and I have been with Prota team for almost 20 years. And I'm acting as product manager and software architect for Prota structure. So after a brief introduction, we will continue with preliminary discussions of the recent earthquakes in Turkey. We will then talk about the observations on the earthquake region. In fact, I visited Antakya, where the devastation was at its peak. And we will continue with the seismic capabilities and overview of assessments and retrofit techniques in Prota structure. Then I will walk you through about the nonlinear analysis techniques in Prota structure. So we are Prota software. Since 1985, we have been providing industry-leading structural engineering solutions to professionals across the globe. And our flagship product is Prota structure. Prota structure suite is in fact broken into 4 different modules coming in a single package. We have Prota structure, which is the core system for modeling, analysis, and design of your structures. It is complemented with other tools. Prota Details is a complete CAD system for automated detailing and drawings. It focuses on concrete detailing and includes a unique design library of calculations for designing things like retaining walls, piles, stairs, etc. Prota Steel complements steel design by automating all the steelwork connection design, providing comprehensive steel detailing and automated connection design of your structures. So there are also drawings and calculation reports within this technology. And finally, Prota BIM allows you to connect with other tools and systems that you may be using, allowing you to communicate with other BIM platforms and software solutions like Allplan through IFCs or ArchiCAD through SAF, Autodesk Revit, etc. Or you can even share an analytical data with SAP 2000 or ETAPS. We have been busy in the last few years expanding our reach around the world that covers 25 international design codes, 9 different languages, from Polish to Spanish, Portuguese, Thai, and English. We have also been busy creating design guides and insights into how the software works, technical guides that cover guidance to from, for example, punching, shear checks, foundation design, earthquake design, etc. So we are now supporting over 85 countries around the world through our partners as well as directly through our offices. And that covers us from Americas through Africa, up into the Europe, across to India, into Southeast Asia. All around the world, we have an amazing user base using our software technology. Unfortunately, we experienced a series of devastating earthquakes on 6th of February. And as civil and structural engineers, we acknowledged once more how important our job is and how it is capable of destroying thousands of lives if our jobs are not done properly. And before starting, I'd like to thank you all amazing people in Ghana. In fact, Ghana was among the very first countries extending their helping hands and prayers to us. Also, Ghanaian people living in Turkey worked hand in hand with us from the very first day to send the humanitarian aids to the region. Thank you all, and on the behalf of the Turkish people, we are very grateful. And also, I want to spare a brief moment here. Please accept our condolences on the passing of Christian Atsu in this unfortunate disaster. He was an appreciated and loved soccer star in Turkey. May his soul and all that we lost rest in peace. Okay, so here on this map, you see the past earthquakes above magnitude 7 in the last 100 years. The 7.7 magnitude Kahramanmaraş earthquake is the second largest earthquake in the history of Turkish Republic, after Erzincan in 1939. In terms of intensity and death tolls, it is the largest. The first earthquake had a magnitude of 7.7, and the hypocenter was located at a depth of 8.6 kilometers. That means it is a shallow earthquake. And only 10 minutes after, there was a 6.8 magnitude earthquake happened. Only after 9 hours later, another catastrophic 7.6 earthquake occurred in the northern part of Kahramanmaraş, again at a depth of 7 kilometers. And we have 50,000 people lost their lives. We have 100,000 people injured. We had thousands of aftershocks. 11 cities are directly affected from this disaster. The population of Turkey is around 85 million, and 14 million people are living in these 11 cities. 20,000 buildings collapsed, and 10,000 search and rescue team members were deployed from 88 countries. So if we talk about the regional tectonics and seismic source, the Anatolian microplate is moving to the west under the effects of African, Arabian, and Eurasian plates. And this movement exhibits itself in the form of two strike-slip faults, namely North Anatolian and East Anatolian faults. Earthquakes happened in the vicinity of Maraş Triple Junction, where the Arabian, African, and Anatolian plates meet. Here you see the map of the East Anatolian fault zone. Major active fault segments are shown in dashed red lines. Yellow solid lines show reactivated segments during this earthquake. The numbers in the rectangles show the year of the last major historical earthquake that occurred at that fault segment and its approximate magnitude. And based on historical data, fault segments ruptured during this earthquake sequence, in fact, are the seismic gaps with tectonic stress accumulating for at least 500 years. And knowing this fact, in fact, Turkey is wired with a fine network of accelerometric stations on different types of soil conditions. And you see here the PGA contours for the first earthquake. PGA contours, peak ground acceleration contours, are an important demand parameter regarding damage, since it is directly proportional to force. We have measured PGA values up to 1.4 G in the first earthquake and 0.6 G in the second one. And the white lines, if you are able to see, indicate the fault rupture in the two earthquakes. The PGA values are specifically high in Antakya region, Hatay region, possibly because of the soil amplification. But peak ground acceleration is not always sufficient to assess the effects of the ground motion. Since our buildings have a certain flexibility, they can experience spectral accelerations greater than the peak ground acceleration. So, for example, here you see the spectral accelerations measured for Hatay city center and its provinces. Also on this slide, you see the collapsed and damaged buildings shown. In fact, Hatay is the most adversely affected city among 11 others. The city center is located on the Amik Basin, which is nothing but an alluvial deposit. The Asi River is passing through the city. And the city mostly has 5 to 15-story residential buildings, which seem to be the mostly affected, as seen in the spectral acceleration graphs. The spectral accelerations exceeded the design basis earthquake in the code, but they seem to be below MCE, maximum considered earthquake, before 0.5 second periods. But basin amplification is clearly seen after approximately 0.5 to 1 seconds. Here is another acceleration spectrum for a particular station that was able to record all 4 earthquake signals. The first 7.7 earthquake and the 6.4 Hatay earthquake, and 14 days later, seem to have considerable amplification effect after 0.5 seconds. And that tells us about building in basins and alluvial deposits. These alluvial deposits always tend to amplify the ground motion signals, and they cause considerable spectral accelerations in the buildings, if not designed properly according to the soil condition. Kahramanmaraş was also one of the critically affected cities, being close to both of the earthquake epicenters. The spectrum for station 6414 exhibits 5 to 6 times greater spectral accelerations that Turkish earthquake code specifies, between 0.1 and 0.5 seconds. But this record is not currently in the AFAD official website. Probably there is an error with the data, and it will be restored back when corrected. But for confirmation, the spectral accelerations in the Kahramanmaraş city center, that is station 4620, and the province closer to epicenter, that's the station 4615, are also plotted. Acceleration values seem to be fitting with dB and MCE code spectra, but still, an amplification, a basin amplification, is observed after 0.5 seconds for one of the stations. This means the buildings that are designed and constructed in accordance with the new Turkish code should be performing well, but old buildings or the problematic building, deficient buildings may suffer from the spectral acceleration as high as 1.25 G. A similar scenario is observed for Gaziantep. In the city center, the code spectra seem to estimate the spectral acceleration demands well. The new buildings should not be suffering collapse from this level of accelerations. The 0.6 G spectral acceleration can cause damage for very old or deficient buildings. That is 2 to 5 stories. I'm talking about the spectral acceleration graph on the right. But for the spectral acceleration graph that's on the left, that's measured in Slahiye, is one of the provinces of Gaziantep. 2 to 5 story buildings suffered a 2G spectral acceleration. And also in Nurda, another province, soil amplification is observed and high spectral accelerations exceeding code values are experienced for 2 to 12 story buildings. That's basically the majority of the buildings. For another city, Adıyaman city center, the buildings with 0.1 to 0.3 seconds periods seem to suffer from a 1.2 G spectral acceleration. After 0.3 seconds, a quick drop is observed. So buildings complying with the new Turkish code should be performing relatively well in this scenario. But again, deficient buildings will be adversely affected. Adana seems to be an interesting case. The observed spectral accelerations are under design and maximum considered earthquakes. And in the city center, the values are also low. Despite this fact, 18 buildings collapsed and 85 buildings are heavily damaged, waiting for demolition. So collapsed buildings have been collapsed buildings are between 12 and 20 stories, and it may not be immediately obvious from acceleration spectra, but when ADRS and spectral velocity graphs are plotted, it seems that buildings with 1 to 2 second periods seem to experience relatively larger demand in the city center. So after this overview, I'd like to show you some of the damage and structural deficiency that I observed in the earthquake region. Let's take a moment together and watch this aerial view that shows Hatay before and after the earthquake. Okay. One of the mostly encountered damages regarding the material quality is the brittle failure of rebars. In reinforced concretes, we don't really expect the reinforcement bars to fail like a brittle chalk. So these rebars are most likely untested and they do not meet the production standards in terms of carbon content. So the rebars should be ductile, not brittle. Majority of the buildings in the region have insufficient lateral stiffness that results in, if not collapsed, a high damage in structural and non-structural members. Unfortunately, it is not a common practice to use shear walls in the buildings in Turkey. If shear walls are used, the ratio of the shear walls to total area is not usually sufficient, and they are mostly used in minimum dimensions required by the code. Also, architectural design do not allow the use of shear walls at the building perimeters. Combined with poor construction and poor supervision, frame-only structures are most likely to suffer damage or collapse. That's what we observed. These two examples are bad habits in Turkey structural system formation. First, due to permit reasons and to enlarge the commercial area at the upper floors, heavy closed cantilever portions are used in the structural system. And also architects prefer a flat ceiling and they want the light when they're inside the room. So this results in discontinuous frames, as you can see on the pictures. So this is a typical floor plan that can be encountered in practice. The only shear walls are utilized in elevator and stair shafts, and they are asymmetrically positioned at the edge of the building, and building floor area is enlarged at the upper floors using cantilevers. And you can also see the beams missing on the axis A, which creates an additional lack of lateral stiffness. And so this results in torsional irregularity and insufficient lateral stiffness, and also causes mode coupling, and this is the observation in one of the buildings. So the building collapsed with a rotational movement. This is a relatively new construction, suffered from damage. When we look at the shear walls closer, we can see inadequate or non-existing wall end zone confinement. The lateral web bars are not anchored and no cross ties are present in the detail. So wall itself also seemed to suffer from a high axial stress, not only at the end zones, but also due to bending, and also in its entire section. The damage is observed when combined with the inadequate detailing and confinement. Settlement and liquefaction issues are also observed on the site. The reason is due to construction on cohesionless alluvial deposits with high water table without any ground improvement, such as jet grouting, etc. And also we have observed incidents of sand boiling and again settlements in the basements, especially in the Iskenderun region. So that means structural design itself is not sufficient. A good structural design itself is not sufficient, but also a good geotechnical design is necessary. If one of them is missing, you will observe damage in the foundation. This picture belongs to a famous residence complex in Antakya, which killed hundreds of its residents, unfortunately. Besides reported lack of detailing and material quality and segregation issues, the structural system itself seemed to have little tolerance for overturning. The three blocks are sitting on a common L-shaped monolithic basement, which is also considered to contribute to the damage, collapse. And due to the aspect ratio of the building, the structural system seemed to lack redundancy. And because of the lack of redundancy, the columns and walls experienced a lot of axial stresses, bending stresses, and they exceeded their capacities. And of course, the old buildings. Turkey has a very large old building stock. According to Turkish Statistic Institution, approximately 50% of the buildings in 11 affected cities are built before the year 2000. This is more or less the same for the entire country. And 2001 is the year when Turkey started utilizing building control regulations in 19 pilot cities. But it was only after 2011 that the building control was in effect for all of the cities. Also, 2001 was the year when a more modern earthquake code was effectively in use. Another important fact is that the ready mixed concrete was actively used only after 1990s. So we expect that the buildings constructed in 70s or 80s mostly use hand-prepared concrete on site, even with the sands coming from the sea. We still have thousands of buildings built before the year 2000. It does not seem feasible to retrofit them within economical limits. So in this picture, you see one of the examples. In the reinforced concrete building on the left, the joints just could not handle the excitation, and the member itself is not damaged, but the joints just failed in a brittle manner, which resulted in collapse, of course. And the building to the right is a masonry building, and most of the masonry buildings in Turkey are unreinforced. They are slightly reinforced only in horizontal and vertical lintels. So these were the observations in the earthquake region. So after this insights on the earthquake that happened in Turkey, I'd like to also cover the seismic code coverage and parameters, what we do in Prota structures to allow you to design safely against the earthquakes. First of all, Prota structure supports a wide range of international seismic codes. The scope includes base shear calculation, irregularity and building checks, seismic design and detailing. Eurocode 8 and national annexes, Romania, Turkey, IBC, UBC, Philippines, Indonesia, India, Thailand, and Peru seismic codes are supported currently. And we are working on Colombia and Dominican Republic codes to implement them in the software. But as you can appreciate, supporting a seismic code is a challenging task and has a lot of details. It's not always possible to support each and every clause by 100% for every structural scenario. We are continually preparing and publishing design guides and knowledge base articles and code coverage documents to be as transparent as possible for the parts of the codes that we are supporting. As I said, Prota structure provides a comprehensive wizard for parametric calculation of elastic and design spectra according to chosen seismic code. For weak soil conditions or for special one-off projects, you can also introduce user-defined site-specific spectra. Prota structure will allow you to use different design spectra for two different orthogonal directions. That means you can use different structural systems in each direction for a more economical design. As a comprehensive solution for seismic design, Prota structure automatically compares response spectrum base shear to the equivalent static base shear and scales up the internal forces and displacements. This scaling is not done up to the 100% of equivalent static base shear. Of course, this depends on selected seismic code. Besides, scale factor changes with the existence of any structural irregularity in the system. Usually, if the structure is irregular, there will be a penalty in base shear scaling by utilizing a larger factor. So RSA scaling factors for regular and irregular cases are user editable in Prota structure. You can override the code-based values by using the options. So as important as the seismic parameters, the modeling for seismic design is also very important. So I will just try to walk you through the advanced model options in Prota structure that will help you to navigate and perform the seismic design. First of all, diaphragm assumption, rigid diaphragm or flexible diaphragm. Assumption is one of the major considerations in building type structures. Prota structure has comprehensive options for diaphragm modeling. Prota structure will automatically detect the existence of one or more rigid diaphragms on a floor level by checking the touching or stepping slab boundaries. You can even exclude some of the slabs from diaphragm contribution. As a result, a floor level can consist of a single rigid diaphragm, multiple independent rigid diaphragms, or free nodes, or their combinations. Regardless of the slab conditions, you can force the entire floor to act as a single rigid diaphragm or no diaphragm at all. If you want to consider the in-plane flexibility of the slabs and other members, you can do so with the flexible diaphragm option. In this case, the floor must be meshed and rigid diaphragm assumption must be turned off for the particular story. You can even adjust in-plane stiffness properties of the slabs. Of course, it may be costly to mesh all stories in a building, especially when it is not really necessary. Prota structure will allow you to mesh only preferred stories, such as basement floors, transfer floors, podium to tower transition floors, etc. Shear wall modeling is a crucial part of structural analysis and design process. That's why we offer different options for shear walls. Rectangular walls can either be modeled with mid-pier or finite element shell members. But while mid-pier option provides an economical and fast way to model the regular continuous walls, they are limited when it comes to irregular discontinuous walls or core walls. Squat walls, whose behavior is dominated by shear action, must also be modeled with shell elements. A good example is, of course, the basement walls. Rectangular wall panels in Prota structure can be merged into complex core walls. Analysis, design, and detailing are done considering the combined section. Core walls are always modeled with shell members in Prota structure, regardless of default wall modeling option. That's because core walls usually exhibit a torsional behavior, depending on the structural configuration, of course. It's also possible to display the internal force diagrams of rectangular or core walls modeled with shells. Group sums are automatically calculated for the core walls, and a single diagram is displayed. So since I mentioned about group sum, what I mean is in order to come up with a single design force or moment in a wall system, we have to use the section cut definitions or group sums or peers. In every software, this is called a different terminology is used. So what we call them is we automatically perform the group sum operation and give you the design forces in a complicated wall shape. So when we export the analytical model to the software like SAP 2000 or ETABS, we automatically assign the section cut definitions and the peer definitions on those software as well. So this is a very strong BIM link, analytical BIM link to this software. Seismic codes may require the use of correct section properties for different member groups and different degrees of freedom. So in ProtaStructure, we provide you with an extensive table for specifying the section modifiers with default values complying with the selected seismic code. You can even use the stiffness modifiers only in some of the load cases. That means you can use uncracked sections for a gravity combination and cracked sections for a lateral combination. ProtaStructure will internally use two stiffness matrices for calculating the results. Depending on the design code and the seismic code you have selected, ProtaStructure saves you time and automatically generates the load cases and combinations. You just need to specify the gravity and lateral loading options. Combination factors are determined based on the selected code of practice. You can then customize the load cases and combinations further. Maybe the most important step for a seismic analysis is the calculation of the masses in the structure. ProtaStructure derives the masses from various sources such as self-weight, imposed loads, user-defined loads, slab loads, infill wall loads, snow loads, and user-defined vertical load cases. In addition to this, each story can have different occupancy and live load participation factors. And at the heart of the seismic analysis is the determination of undamped free vibration modes of the structure. These modes are used in equivalent static or response spectrum analysis. ProtaStructure automatically calculates the vibration modes by a 3D subspace iteration eigenvalue analysis. Dominant modes are detected and sorted with respect to their mass participations. Cumulative mass participation is also checked in response to spectrum analysis. Masses can be lumped or distributed with rotational inertia, and 3D torsional modes and local modes can easily be detected. The calculated period of vibration is automatically compared with the upper limits in the seismic codes, which are calculated by empirical formulas or Rayleigh formulation. The simplest method of base shear estimation is done by the well-known equivalent static load method. This method makes use of the dominant mode of vibration at each direction. ProtaStructure automatically calculates the base shear and distributes it to the story levels by using seismic mass and the story heights. If there are multiple diaphragms or free nodes, loads is shared among them. Accidental eccentricity is automatically calculated. Irregularity penalties are automatically applied. Unlike equivalent static load methods, the response spectrum analysis can take the higher mode effects into consideration. The model responses are combined with CQC method. ProtaStructure can incorporate the additional eccentricity in model analysis by introducing the eccentricity load vectors during the analysis. Code checks such as RSA to equivalent static amplification and cumulative mass participation checks are automatically done. And since the results After the CQC combination, the sign of the results are lost, and you can choose whether to use the dominant mode signs or absolute values for forces and displacements. Vertical earthquake components can be prominent, especially if building has large spans, transfer beams, transfer floors, long cantilevers, discontinuous columns, etc. The vertical component can cause unexpected axial strains and vibrations. Seismic codes usually calculate the vertical component as a percentage of horizontal component and amplifies the gravity load case results. Prota structures follows this simplified methodology as explained in the codes. But for some cases, codes require a vertical model analysis to take the vertical components into consideration by the help of a vertical acceleration spectrum. But this methodology, of course, requires a careful identification of vertical masses and detection of necessary vertical local modes. Seismic design of buildings with basements require special attention. Since they are usually underground, the earthquake forces calculated for the basement stories must be handled differently and integrated into superstructure. Besides, basements are usually excluded from irregularity checks. On top of this, some of the seismic codes require using a different stiffness modifier for basement walls. Besides, because of their aspect ratio, the basement walls must always be modeled with finite element shell elements. That's why we support a dedicated basement wall type in Prota structure. Since the stiffness properties of the basement stories are different than the superstructure, the seismic codes usually require a two-stage analysis of such structures, where basements and superstructure are analyzed separately and the results are combined. Prota structure can utilize different mass and stiffness matrices to perform a two-stage analysis. In the first analysis, basement masses and seismic loads are eliminated or ignored. Only the mass of the superstructure is used. Stiffness of the basement story is still considered. In the second analysis, mass of the upper structure and the building is ignored, and only the loads in the basement story is calculated. But of course, stiffness of the upper story is still considered, and then the results of these two analyses are combined. Especially for the buildings with basements, the determination of building height is a vital step. In Prota structure, the user specifies the number of rigid basements. In other words, user decides the building height and building base. However, the basement stories need to satisfy certain conditions in order to qualify as basement. One method is to compare the superstructure period to the entire structural period. Of course, the rigid basements should also physically satisfy the required conditions. That means they should have surrounding basement walls and have a significant stiffness difference than the upper structure. After the verification of building height and building base, Prota structure will calculate the seismic loads considering the basements and exclude the basement stories from irregularity checks. Building effective top story is as important as the basement stories. Mostly the top stories include elevator maintenance shaft or similar mechanical facilities. The supporting structure at the top story usually has lower stiffness and lower mass. Performing irregularity checks, including the maintenance story, may be unrealistic depending on the project. So Prota structure provides a tool for engineers to use their engineering judgment and set the effective top story of the building. but effective top story stiffness and mass are still considered in the analysis, but they are excluded from irregularity checks. Protostructure will check horizontal irregularities and apply the penalties automatically for equivalent static load method. If floor torsion irregularity exists in the structure, protostructure will increase the additional eccentricity and repeat the analysis with the new eccentricity value. In case of excessive floor torsion, equivalent static method will not be applicable and protostructure will warn the user. Diaphragm discontinuity must be detected by the engineer, but protostructure provides the necessary tools to handle the cases where rigid diaphragm assumption is not valid. As I said before, protostructure will check the slab discontinuities and exclusions and decide on multiple rigid diaphragms and free nodes on a floor level. Flexible diaphragms can also be used where the rigid diaphragm assumption will not be valid and in-plane stresses need to be evaluated. For buildings having structural frames non-parallel to the specified earthquake direction, 30% of the other direction can also be applied in the combination wizard. Protostructure will also check vertical irregularities and present a detailed report. Soft story, extreme soft story, irregular vertical distribution of mass, weak story, extreme weak story are among the vertical irregularities that can be checked automatically after the analysis. As I specified before, basement stories and effective top stories are excluded from irregularity checks. Relative drift checks are always a major part of seismic checks and a strong indicator of damage vulnerability. Protostructure performs the relative drift check for each story and presents in a tabular format. The critical member exhibiting the maximum displacements is indicated in the report so that you can review it in your model. And the drift check in protostructure can also recognize and identify the intermediate nodes of a column that's inserted as a single piece from top to bottom. Second order effects requirement is another important post-analysis check. It evaluates the moments created by the weight of the structure under lateral displacements to the moment created by the story shear. If the ratio is too high, then the structure may be susceptible to second order effects and a detailed review must be done. For the seismic overturning check, as its name implies, it's a stability check under seismic loads that compare the overturning moments to the resisting moments. Protostructure can perform strong column checks of reinforced concrete and steel special moment frames according to ACI, Eurocode, and Turkish earthquake codes. In addition to this coverage, strong column and weak beam reports are now developed from scratch to include more visual components with intelligent notifications. For flat slab buildings or for buildings where we have floor plan irregularities, such as diaphragm malformation, large openings, or discontinuities, we must check the safe transfer of lateral inertial loads from slabs to the walls. This check simply calculates the unbalanced shear force between top and bottom shear wall and checks if this is resisted by shear friction on the shear wall slab overlapping surface. If not, additional dowels are calculated. For excessive situations, additional longitudinal bars are calculated in the connecting beams. But the calculated additional bars must be manually provided by the user. For the cases where rigid diaphragm assumption is under question or not valid, we must check if the lateral inertia forces are transferred safely by the floor. For this purpose, the in-plane tensile and compressive and shear stresses should not be exceeded. Excuse me. A protostructure can also calculate the seismic forces acting on non-structural members and their connections to the building. All you have to do is to specify the non-structural member and their properties, and protostructure will automatically calculate the story accelerations acting on that particular story, and then you will automatically calculate the forces acting on the non-structural member so that you can design their connections. And finally, to avoid pounding damage in adjacent buildings, we must provide spacing between structures. If you need to design the seismic separation between two buildings, you can use the seismic joint design tool in Protostructure. With this tool, you can either load the displacements of an existing Protostructure model, or you can enter the second model's displacement values manually. So using the displacements from two separate models, Protostructure will calculate you the necessary amount of seismic gap between two structures. So these capabilities brings us to now a different topic. We use these capabilities, of course, for the new buildings and for assessment and retrofit as well. So in terms of assessment of existing buildings or performance design of existing or maybe the new buildings, what we offer to our users, first of all, we offer a practical and seamless workflow for assessment and performance-based design. If you have detailed blueprints of a building, you can enter the estimated or exact reinforcements in the members. First of all, modeling an existing building is no different than modeling a new building. All you have to do is just define the geometry and put the existing rebars, or if you don't know anything about the existing rebars in the existing building, you can just estimate the rebar. Most of the time, existing buildings suffer from corrosion, and if you have blueprints of the building, the existing rebars may not be complying with the rebars in the blueprints. That's why we introduce corrosion and rebar realization factors. And you can enter these values for each and every member so that their capacities are reduced accordingly. And also you can use a global coefficient for building information level to factor down all the member capacities, because before starting the existing building assessment, we have to go inside the building and collect information. If the information we collected from the building is a detailed information that we know everything about the building, blueprints, if we have taken samples, enough samples from the concrete, enough observations from the rebars, we can say that the information level is a detailed information level. But if we don't have detailed information, you can just use a global coefficient less than 1 to factor down all the member capacities to cater for uncertainties in the material grades or geometry or reinforcement. And also in Protostructure, you can assess the structure simultaneously for different performance targets. And assessment and retrofit workflow is same for all seismic codes in general. In addition to this, plasticity definitions, time history and pushover analysis procedures are also usually generic. However, member-by-member assessments and performance limits may vary in different seismic codes. Currently, Protostructure performs the member assessments only to the Turkish codes. So we support 4 different analysis and assessment techniques. The first one is maybe the most approximate method is displacement-based linear elastic method. It deals with relatively regular structures with high model mass participation. In this analysis, yield curvature of the members are obtained with a nonlinear fiber section analysis. Then a linear elastic analysis is conducted under elastic spectrum with no eccentricity and no importance factor. Then plastic rotations are estimated from linear chord rotations and yield curvatures. There are also additional checks ensuring ductile failure of the members. Then member plastic rotations are compared with code-specified limits. Risk assessment is a relatively faster method to decide the risk status of existing building. This is very specific to Turkish construction practice because we need a very fast method to assess our old building stock. The other analyses are single mode static pushover and nonlinear time history analysis, and these are the well-known analysis techniques in the industry, which are of course quite generic in conduct. However, material nonlinearity definitions may vary in different seismic codes. Currently, material nonlinearities and assessment is again done to Turkish codes. One of the strengths of Protostructure resides in the ability to conduct nonlinear pushover and time history analysis for assessment and performance-based design. And we achieve this by the OpenSeas integration. As you know, the OpenSeas stands for the Open System for Earthquake Engineering Simulation. It's an open source software for simulating the seismic response of structural and geotechnical systems. But of course, nonlinear analysis requires a wide range of algorithms and solution methods, and OpenSeas provides a nonlinear static and dynamic methods for that purpose. In Protostructure, we communicate the analysis model to OpenSeas with the help of TCL files. In addition to the detailed analysis model, nonlinear material properties are also automatically calculated and added on top of this model. The entire structure is then ready for a performance analysis. For a successful OpenSeas integration, considerable amount of pre-processing and post-processing is necessary. All the material nonlinearities have to be generated and sent to OpenSeas. Column, beam, and wall sections can be modeled with fiber elements and analyzed with state-of-the-art numerical techniques to derive the moment curvature relationships. Confined and unconfined concrete regions can be specified, and strain hardening in steel bars, steel material, can be taken into consideration. For columns and walls, a finite length hinge zone model is used with 6 integration points. Force deformation relationships for integration points are obtained from fiber section analysis. Single mode static pushover analysis is performed using, again, OpenSea's integration. Parameters such as number of steps, target displacement can be controlled by the user. After the analysis, the capacity curve is obtained. Users can specify the monitored node for which the curve will be generated. Results can be examined at any desired step. A detailed performance assessment report is generated after the analysis. A vital step after pushover analysis is to find the demand that a target code spectrum requires. It's also known as the performance point. After plotting the capacity curve, the protostructure can detect the target displacement value according to the FEMA Eurocodes and Turkish Earthquake Codes. A nonlinear time history analysis can be performed, again using OpenSea's integration. A set of multiple ground motions can be applied simultaneously in X and Y directions. As specified by the earthquake codes, the ground motion application direction is rotated by 90 degrees and analyses are repeated. The selection of suitable ground motions is up to the user, of course. You have to go to the ground motion database and select the suitable ground motions for your structure and for your structure's location. And in this selection, parameters like fault mechanism, soil properties, magnitude of the considered earthquake are also important. But the selected ground motion records are automatically scaled by protostructure using this simple scaling method. After the time history analysis, the results from multiple ground motions are automatically post-processed. The average values or absolute maximum, the average values of absolute maximum responses are extracted and used in performance assessment. You can also use maximum values if you like. And after that, a detailed performance assessment report is created. And to visualize the assessment results, protostructure can present the member damage regions and risk status by the new color-coded visual interrogation options. So after talking about these analysis and assessment methods, I want to briefly talk about the retrofit techniques, and that will also end my presentation. So one of the mostly utilized retrofitting strategy is to use reinforced concrete walls inside the existing frames. This method improves the overall lateral behavior of the existing building, especially by limiting the lateral deformations. In protostructure, you can insert retrofit walls in your existing structures. Modeling of the existing structure is no different than the new building, as I have specified. Before the assessment, you must provide preliminary longitudinal and horizontal bars in the retrofit walls. After the assessment, you can design the top and the bottom dowels that connect the retrofit wall to the existing frame. Of course, detailed drawings and quantity takeoffs can be done in Prota details. Reinforced concrete column jackets can be used to locally improve the axial loads and moment capacity of an existing column. Depending on the extension of the longitudinal bars into the upper story, the reinforced concrete jacket can resist moments or not. This can be set as an option in protostructure. If the existing column is too damaged or weak, you can also delete the existing column from the model, if you like. Protostructure is also capable of retrofitting and assessing beam and column members confined with carbon fiber reinforced polymers, which we call CFRPs or FRPs. The FRP confinement has a positive effect on the shear resistance and axial load capacity of the members because of the confinement, extra confinement they provide. Currently, Protostructure can consider these effects according to the Turkish codes only, and US and Euro codes guidance will follow. So base isolation is a separate topic in itself. We have to talk about base isolation for maybe a couple of hours. Base isolation can be used as a retrofitting strategy or can be used as a strategy in the new buildings. But currently, we do not really prefer base isolation for existing buildings, although we have examples of it in the world and in Turkey. If the building is too weak, base isolation, retrofitting it with base isolation may not be economical and may be really difficult in practice. And also, the building may not be strong enough to resist the activation force of the isolators or even the lower accelerations in the upper story. So base isolation is usually a good solution for the brand new designs. What base isolation does is base isolators simply concentrate the lateral deformation at a relatively soft isolation layer. They also elongate the vibration periods of the building so that less spectral accelerations are experienced overall. However, soil conditions must be carefully investigated for a possible resonance situation. Besides, isolators introduce additional damping to the superstructure and they help reduce the spectral accelerations in the upper structure and they help reduce the relative drifts in the upper structure, allowing an almost rigid body oscillation. In Protostructure, you can insert seismic isolators anywhere on the columns, since the base isolation is not necessarily at the foundation level. First of all, you must, before designing your structure with base isolators, you must have decided on the isolator units, layouts, and lateral and axial capacities before modeling them in Protostructure. Please note that currently you can only perform a linear elastic analysis with base isolators in Protostructure. That means they can be used to design and verify the upper structure. This example is a new hospital design. Here you see the base isolated model on the right and the conventional fixed foundation option on the left. The base isolated model clearly exhibits a rigid body deformation at the superstructure, as you can observe. Well, this ends my presentation today. I'd like to thank you so much for reserving your time and this session to me, and I'd like to thank you for your participation again. I now would like to hand over to Abel for introduction of other speakers. Thank you very much. It was a pleasure for me.
Thank you very much, Engineer Mustafa, for that insightful presentation. Now, the first one was fantastic. The first presentation was phenomenal. Everybody understood it clearly. We could relate. We saw all that went on. And look, what even touched my heart was the before and the after scene. When a beautiful city like that was brought to ruin, when such things have gone on. We too, we have buildings, we have old buildings like that in Ghana. We have old buildings, and I think there's going to be a lot of work for the district assemblies or the municipal assemblies to also take a cue from them. We'll be sharing some of these things as we move on. So I think on this note, we'll be looking to invite our second speaker. But let me tell you a bit about the second speaker before I hand over the mic to him. Okay. So, ladies and gentlemen, please allow me to introduce to you Engineer Kwabena Bim. He is the Chief Executive Officer for Associated Consultants Limited, with over 30 years of experience in the field. Engineer Bimpo is a highly experienced and knowledgeable highway and structural engineer who has worked on numerous projects throughout his career. He holds a BSc degree bachelor's degree in civil engineering from KNUST, master's degree in road engineering from the Netherlands, and also as a fellow, he's also the current president of Ghana Institution of Engineering. you get it. And so if, let's say, as we have this event, we wanted to invite somebody. He is the president of the Ghana Institution of Engineering, GHI, and a member of the Institute of Directors. Engineer Bimpo is an accomplished and respected leader in his field. With his field, he has gradually risen through the ranks with exceptional performance on all projects, and recently managed and designed the construction of Ghana's first 4-tier interchange, which we call the Pokwase interchange, which has won international recognition. But beyond this, beyond his technical expertise, Engineer Bimpo is also a strong advocate for diversity and inclusion, and is passionate about creating an innovative culture where everyone can bring his authentic self to work each day. Please, ladies and gentlemen, join me in welcoming Engineer Kwabena Bimpo.
Thank you very much, Abel. I was just wondering where you got all this information from. But in any case, I want to thank you and the other organizers for inviting me to make a presentation, even though it was a very short notice. And I have a research assistant who has assisted me because I had him, that is Engineer Eric Sentima Boaje, who is a principal consultant at Associated Consultants, and he was part of the bridge design team for the Pokwase interchange, which you mentioned. So the outline of this afternoon presentation is as of here: introduction, understanding Ghana's earthquake hazard, design of buildings to resist earthquake forces, which has been very well done by our previous speaker, and then some conclusions. But by way of introduction, I would like to mention that Ghana in 2019 came up with what we call a framework for refocusing Ghana's earthquake preparedness and response. Because you learn that Ghana or Accra, southern Ghana, is also considered as an earthquake-prone area. And for those of you who are in Accra, we've experienced some earth tremors in the past few years. The last major earthquake was in 1939, and I'll be showing that very soon. But then let us have some perspectives on earthquake. And I'm not going to go too much into the details, but just to scratch the surface, because I must mention that I am not an earthquake engineer like our previous speaker, but have had opportunity of studying the incidence of earthquakes vis-a-vis how we should respond as a people. Because if we do not have education, the engineers may have all the understanding, but then the people must understand what earthquake is. And we say that earthquakes are a natural phenomenon which occur in large parts of the world. It doesn't only occur in Turkey, very large parts of the world, and I'll be showing that very soon. It is also caused by the movements of the earth. And this is because of an abrupt release of strain energy that has been accumulated over a long time, that we'll be looking at very soon. And if you look, I just looked up, the statistics from 1900 to 2016. China has had the highest amount of earthquakes of about 157. So between these two times, and this is from Statistical Research Department. And if you look at the top 5 countries with the most earthquakes, you have Indonesia, Iran, Turkey, and Japan. And the death tolls within this period has been over almost 900,000. And as we learned this morning, in Turkey alone, this year, 50,000 people lost their lives. So earthquake is something that has to be taken very seriously. And there's the popular saying that earthquakes do not kill. Earthquakes do not kill, but buildings do. So this is where we come in. We should not see earthquake or flooding, or for that matter, any other natural disaster as the enemy. But the buildings that we place on them, which are subject to earthquakes, are the ones which kill. So, because you cannot do anything about the earthquakes, you and I cannot do it. It's a natural phenomenon, but we can do something about the buildings that we design. And this morning, it has been demonstrated to us that there are methods that we can use to ensure that our buildings are safe. And there's something we call the ring of fire. For those who know a little bit of the world, earthquake regions in what we call also the second Pacific seismic belt, where about 81% of the planet's earthquakes occur. And this, when you go out onto the net, there's a place where you will see the occurrence of earthquakes. And this morning, when I checked, okay, on 8th May, just 2 days ago, there was an earthquake of magnitude 5.1, in Tonga. 5.9 occurred in southeastern Pacific rise. Philippines had 5.2. There has been 5.2 in Chile. Russia had Japan. So you see, every time there is earthquake happening, and this is where the ring of fire, comes into place. So we need to understand what earthquake, is. And to understand earthquake, it is important that one looks at what earthquake is. It is necessary to look at the origin. And like I said, I do not intend to go too much into the details. But then when we talk about the origin of earthquakes, this is a question that a lot of people have asked for more than 2,000 years. It is only in the past 150 years that mysticism, and I know that, what we call the mystics in Africa, in Ghana, this thing would welcome very sure. We say, oh, maybe this is caused by some spirits. But I can tell you that there's a realistic scientific scrutiny, and that has caused or brought about the understanding of the mechanism of earthquakes. Also, a geologist who lived in the 1800s, G.K. Gilbert, he was the first to suggest that earthquakes were the result of displacement along geological faults based on observations of the Wasatch Mountains in north-central Utah, USA, in the 1880s. And when we say faults, we hear about faults. Faults are basically fractures in the Earth's surface, along which the displacement, occurs. So you can have a crack, or let's call it, let me use crack in the rock forming the Earth's surface, and that's may constitute a fault. So these are fractures in the Earth's surface, and if you subject this, or you probably may have observed that when you subject, say, a rock or concrete to a compression test in the laboratory, you find that there's a crack or shear failure. This is the kind of thing that we are talking about. It is also the movement or displacement along geological faults. And this, if this were occurring continuously, then there wouldn't be any major earthquakes. Nature, however, does not permit this, because most faults become locked. Such forces will cause displacement. I always try to use the one being behind the door, and somebody is pushing the door, you try to resist that movement. Now, if the person leaves the door, you know what is going to happen? There's going to be a release of that energy that you have been using to push the door, to close it, or to open it for that matter. And this will release the energy. But in the case of rocks, what happens is that once the rocks are able to, to fill, the joint is able to fill, then there's a release of a significant amount of strain energy that has been stored in there. And this also, that sudden release of strain energy is what causes earthquake. And of course, once there's earthquake, there's going to be shaking. There's a radiation of seismic waves, and they will propagate in all directions. They travel outward from the source of the earthquake along the surface through the earth at various speeds, depending on the material through which they move. And some of these vibrations are of high enough frequency to be even audible. Sometimes, when even in Ghana, when there is a little bit of tremor, we feel and we sometimes hear whatever is happening. So there's a kind of trembling of the earth. Now, I do not intend to go too much into this detail, but then I know the slides could be shared. But then the observations of the aftermath of the 1906 Francisco earthquake allowed Reid in 1910 to propose the theory of elastic rebound to explain the mechanics of earthquakes. So if you look at figure 1B, you see that when there's an earthquake, there's there's movement between two sections. So if you see the first one at the top is straight, but the second one moves independent of the first one. That is the one colored brown and the other one colored blue. So you can see that there's a deformation of the line. You could also have subsidence or flip. And these are all parts or the explanation of how earthquakes, happen. This is just to illustrate it. Now, I do not want to go through all of this, but then just to show that when these forces are applied, there's the shear strength of the fault is reached up to a point, then it ruptures suddenly. And once it ruptures, there's a release of this strain energy, and that is what is going to generate the earthquake. And there's going to be a displacement. I do not want to go into this, but then by definition, an earthquake is the vibration, sometimes violent, of the Earth's surface that follows the release of energy in the Earth's crust. This energy can be generated by a sudden dislocation of crust segments, volcanic eruptions, or even man-made explosions. So it is not always generated just by the natural. Sometimes, maybe as a result of mining activities, you can trigger an earthquake. And based on the medium in which these earthquakes waves travel, they can be classified as body waves or surface waves. Now, I just decided to have, to show us the seismicity map of the world, just to illustrate to us that earthquakes are happening everywhere. You can see Greece, Tajikistan, China, Philippines, Indonesia, and all that. And they all, again, we do not want to go into plate tectonics, which we all know about. I thought that the first figure I was going to talk about plate tectonics, but then there are active faults along where he mentioned the Eurasian plates, the Arabian plates, and the African plates. So these are some of the issues that lead to to earthquakes. Now, the question that one may ask, which again has been explained, are how earthquakes occur. Their characteristics. We have the intra-plate earthquakes, like between plates, and these happen. These are not that that is the intra-earthquakes are not that common or as frequent as or as large as those along the plate boundary. So if you say intra, that is within the plate. So if you take, let's say, the Eurasian plate, you can have some earthquakes occurring within that plate, but these are not as frequent. Then they tend to occur in soft weak areas of plate interiors. But the most important ones, and of course the one we see in Ghana, are mostly intra-plate earthquakes. Now let us also look at the primary effects of earthquakes. This is where we are, as engineers, should be worried. The primary effect of an earthquake is the ground shaking, and the nature of this ground shaking that occurs at any given location depends on the effects of the earthquake source. That is the fault, the path through which the waves travel, and the site on which the eventual ground shaking occurs. So, for instance, if it is on soil with high, and I think that the first speaker mentioned it, where you have high water table, you have silty soils or sandy soils, then it could be subject to liquefaction, where the soil loses its shear strength, within a very short time, and that can lead to subsidence or the collapse of buildings, or whether it is on rock and all that. So the soil or rock on which our buildings are located are also important in the response of the building to earthquakes. Okay. More, we have the effect is generally severe at the point directly above the focus, that is in areas around the epicenter, and as the distance increases from the epicenter. So, for instance, in Ghana, we will see that the epicenter was so many kilometers away in the sea, or at Nyanyano or at any other set place. Then you could also have a local side effects, and this is what I was explaining, where you have shorter or less compact grounds, or even further away from the epicenter, it may have higher intensity or amplification and longer duration of the shaking, and therefore have higher damage potential. I think that in the earthquake, in the Turkey earthquake, that was also mentioned, where the amplitudes or the effects of the earthquake, very, very small, but then that caused extensive damage. So the local effects or the soil under which the structure is located is also as important. And these are some pictures showing, and I know that when you look at the rubble, you understand that if we are having such things in other countries where a lot of data and good designs are taking place, then in Ghana we have to be very careful. And as we explained, within the last few weeks, we've had 4 collapses. If it is collapsing when it rains, then what will happen if there are lateral loads or ground shaking? The middle one is what happened in there's a Kobe earthquake in Japan, and then we have rail lines buckling as a result of earthquakes. The earthquakes could also lead to fires, tsunamis, and variety of ground effects, and these are secondary effects. We can have landslides, rock falls, liquefaction, as I explained, or the surface rupture. So now let us, having this background, let us look at the Ghana earthquake. And I'll take time here. Geologically, Ghana lies along the southeastern margin of the West African Craton. And the Kapim mountain range, which lies in contact with the West African Craton, is known to contain a number of faults which have been responsible for several earthquakes in Ghana. And you can see, a Google Earth satellite image showing southern Ghana, the West in West Africa, and the mid-Atlantic ridge, and its transform faults and fracture systems. And I brought this to illustrate the fact that Ghana, and of course we all know that we've been experiencing some tremors, but Ghana has experienced a lot of earthquakes in the past over 100 or 100 years, and it is important that as engineers or practitioners we are mindful of this. So I just want us to look at some historical records. And despite that we are very far from any major known tectonic interplate boundaries or active volcanogenic regions of the world, southern Ghana has been seismically active for centuries. Previously recorded damaging and destructive earthquakes have been reported in places wide apart in southern Ghana, most notably from the southwest in the districts of Atim and Elmina, to the southeast in Accra, and all the way to the whole district. Very, very wide, and this we are talking about 600 kilometers. The earliest known record of earthquake in Ghana is from 1615, but there's insufficient information to determine the magnitude of the earthquake. In 1986, Adams compiled a historical record of earthquakes from 1636 to 1973 using newspaper reports, missionary records, and other sources. The historical record includes 4 major destructive events. I know that the one that we remember most is the 1939, but then there have been also, some earthquakes in the past, when, from the 1630s to 1788. Ghana, we also have instrumental records, that is records taken up. And again, like I mentioned, this is information that is contained, in the framework for earthquake response in Ghana that was commissioned in 2019. So I'm taking a lot of information from there for our info, and we can always go to that document and get more detailed information. But then we have instruments, instrumental records by the Ghana Geological Survey Department, and we have seen quite recently some smaller earthquakes in the past few years, just reminding us that earthquakes are very, very close to us, and we have to take precautions in our designs and not to just leave them to chance. So these are just some of the historical records of earthquakes in Ghana, all the way from 1636, and the dates are there, the location, and then the magnitude on the Richter scale. So you can go down all the way to the high. Well, we had one in 1862, 7.1, and then the 1931 is the something that we all refer to on 22nd June 1939. We refer to as the major earthquake in Ghana, 6.5, where we have 1,500 houses had to be demolished, 600 required repairs to be habitable, 16 people died, 183 were injured, and over £1 million worth of property was damaged. Now, if in 1939 this happened, can you imagine what will happen when, or if an earthquake hits Accra or southern Ghana around this time? This is going to be disastrous. So it is important that as engineers, we continue to bear in mind that whatever we do would require some introspection. Now, when we look at the instrument records to 6th March 1997, I remember this very well. There was a structure very close here at Kokomlemle. It collapsed. And that was only magnitude 4.8. You get it? And if you look at the recent earthquakes from 1997 to 2019, they have been very low magnitudes. And if this is causing some cracks in buildings, then what will happen if something like what happened in Turkey happens in Ghana? Again, I cannot stop talking about the fact that there's a need for us to be careful. I'm not going to go through all this because this is going to be made available for you, but just to recognize that our seismicity in the southern Ghana is caused by a fault system of the Atlantic fracture zones, which are dominated by the Romanche and the St. Paul's fracture zones. We have 2 recognized seismogenic regions, that is Axim and Lumina seismic and the Accra Hole seismic. So so you can realize that the whole of southern Ghana is within the earthquake zone, and it is important that we take precautions, in whatever we do. When you talk about earthquake resistant design, you do not design earthquake proof buildings. It is only resistant, and we have just gone through the methods by which we could do that. But then the basic principle is that there's a need for our designs to prevent building collapse during earthquakes and to minimize the risk of death or injury to people in or around those buildings. Because earthquake forces are generated by the inertia of buildings, and the inertia of buildings dynamically respond to the ground motion. And in terms of the dynamic nature of that response, due to the earthquake loadings and from other building loads, you being the designers probably may be tempted to consider earthquakes as a very strong wind, and this must be avoided. This must be avoided, and I think we have seen that in the presentation that is that was given to us. The building, that's the dynamic characteristics of our building, are fundamental to the structural response, and that earthquake-induced actions can be mitigated by design. The earthquake-induced actions can be mitigated by design, and we have seen how Prota structure is able to handle that, for us. It says that a good earthquake engineering design is one where the designer takes control of the building by dictating how the building is to respond. And this is achieved by the selection of the preferred response mode, the selecting zones where inelastic deformations are acceptable. Again, this has been demonstrated to us, in the software that was shown to us, where, by the first speaker. And then there are desirable mechanisms which are sufficiently strong to resist normal imposed actions without damage. At the same time, they are capable of accommodating substantial inelastic deformation without significant loss of strength or load carrying capacity. There are some mechanisms that have been found to generally involve the flexural response of reinforced concrete and steel structural elements, or the flexural steel downward response of timber connections. Undesirable post-elastic response mechanisms within specific structural elements have brittle characteristics, and they include shear failure within reinforced concrete, reinforcing bar bond failures, loss of axial load carrying capacity, or buckling of compression members such as columns. But then, what was shown to us, we saw the snapping of reinforcement. I have never seen anything like that before. It is not that the steel is bending, but it is snapping. And this is something that in Ghana, because of the kind of materials that are being used, especially for our construction, we probably again have to be cautious, because if steel can snap as if it has just been sheared, then it means that with a lot of this poor reinforcement on our markets, what is going to happen if an earthquake occurs? So this is something that we need to, yes, our concrete, that are now with the collapses that we are seeing, if you go to the site, you'll find out that the concrete, which is always the first line of attack, is very weak. Very, very weak. So these are things that we need to also be careful about. The seismic structural performance requirements of buildings are often prescribed within our national codes. So for instance, clause 17.10.3.1 of the Ghana Building Code prescribes that a building categorized as class 1 is to retain its amenity when subjected to frequent events of moderate intensity earthquakes. Furthermore, it is to remain stable and avoid collapse during rare events of high intensity earthquakes. And in order to comply with the mandatory provisions of our national building codes, the following requirements are to be satisfied. We know of the stability limit state. We know of the ultimate or survival limit state. These are things that we have to ensure that the building response remains predominantly elastic. Because if it moves into inelastic response, then we will have a lot of damage, in our structures. And for also to avoid sudden collapse of our building, and which has a risk to the safety of the people in, because the building is not what the earthquake is not what's going to kill us, but then it's the building. So if we are designing for ultimate or survival limit state, then it reduces the risk to the safety of life within such buildings, and building collapse will be avoided. There are various types of earthquake resistant structural systems that are available, and I'm not going to go through again just for the sake of time. We have the moment resistant frames, we have shear walls, which have been explained, we have brace frames. Brace frames, I think that there's one structure in Accra, the airport, which shows this, and that building also has base isolators. That is the #1 airport square. It has bracing, and then it has base isolator. Then what we use in Ghana, there is a confined masonry walls, where you construct your walls and then you box your columns in there and construct. It is said that it has some level of resistance to earthquake. But at the end of the day, it is all about how the construction is done. Because if you have all of this and your concrete is, you don't have adequate reinforcement, then in Turkey, the most frightening and terrible after effect earth causes accumulated over time of the earth can cause serious damage to buildings and other infrastructure. If an earthquake occurs in a populated area, it may cause many deaths and injuries and extensive property damage. We cannot prevent earthquakes from occurring, but we can build better to avoid building collapse and as a result, loss of life. The seismic performance of buildings depends to a large extent on the building configuration chosen. It is therefore important that architects are aware of the issues involved and they work closely with structural engineers at the conception stage. And if the configuration chosen is wrong, the building becomes difficult and expensive to design, and the results may not be completely reliable. Ghana's earthquakes are interplate earthquakes. They are caused by fault systems in the Atlantic fracture zones. Ghana has two recognized seismogenic regions. We've mentioned that, and Accra whole region continues to be seismically active, and the causative forces are responsible for the majority of Ghana's past and current earthquakes. The Accra-Tema corridor of the Accra whole seismic region is Ghana's most active and vulnerable earthquake zone. I thank you very much for your audience.
Okay, so thank you very much. Thank you very much, Engineer Bimpong, for this wonderful presentation. Ladies and gentlemen, it's my pleasure at this moment to introduce you to the highly accomplished engineer, Engineer Henry Kojo Boateng. Engineer Boateng is a fellow of the Institution of Engineering and Technology, Ghana, and also the current president. So I know you'll be wondering why we brought the current president of GHI, the current president of IET. In fact, we really want to give you nothing but the best. So Engineer Boateng is currently the president of IET Ghana. He has an impressive background with over 20 years of experience in the engineering field. Engineer Boateng holds multiple degrees, including Masters in Engineering in Building Services Engineer with Management, MSc in Procurement and Management, BSc Building Technology and Licenseship in Construction UK, and Investigative Accounting and Forensic Auditing from Ghana Technology University College. Sorry. He has worked on large construction projects from conception through pre-tender to post-tender activities and has been involved in the supervision and coordinating of all technical aspects of field engineering assignments, including quality control compliances. Engineer Boateng has also served on a number of committees at government and other built environment agencies, including the Strategic Planning and Ghana Chamber of Construction Industry, Licensing and Registration of Engineering Council, and the Enforcement of Technical and Vocational Education and Training. He has established District Works Department for Sunyani West and Banda, trained construction industry professional, and manage and engineer landfill sites for waste management. Engineer Henry Kojo Boateng is also known for his involvement in investigating the circumstances leading to the collapse of the Church of Prosperity building at Achimbatabi in 2020, where he served as the chairman of the investigative committee. He is a member of the Ghana Institute for Construction and the American Society for Civil Engineers, AEC. Please join me in welcoming Engineer Kojo Boateng to take over from me from this point.
Yeah, thank you, Ibo. Thank you. I think previous speakers have talked a lot about the earthquake happenings in the world and the causes, and our structures which are collapsing. I sought, you know, I'm a public servant. I sought permission up to 12 noon, but it's now 12:20, so mine is going to be very brief because the time given was too short. I asked a fellow engineer to prepare a slide for me in the person of Engineer Davo Wonder. So straight away I'll go through. Yeah, for the Turkiye Earthquake Review lessons for Ghana engineering professionals. You can see a picture of a woman in red crying. This depicts our Ghana culture, our culture, when one is bereaved and we are mourning. That's how we dress. Now, in the introduction, earthquake is a natural phenomenon that occurs without warning. I think the previous speakers talked about it. And mostly brings about failure of buildings, damage to properties, and loss of life and injuries. We all witnessed what happened at Turkey recently. Now, Engineer Bimpong also talked about what has happened in Ghana since even to the 16th centuries. But I took mine from 1931, which okay, it was very, it caused a lot of damage and a lot of structures collapsed. We had one 8th January 1977, which we all witnessed. I think by then I was at National Theatre and most of the glass fell out. 6th March 1997, this happened and the effect was very much at Bawi. 26th September, we had at Takrady and Wejabami. Because we know it runs through Axim, Elmina, Accra, all up to O. These are the major areas we do experience these tremors. Now, effect of earthquakes in Ghana. Effect of earthquake in Ghana is mostly damage of properties, of loss of life, as I said. In the recent happenings at Turkey, we know what's happened to our dear brother, Christian Achu, who was one of our famous footballers in Black Stars. Not only death, we also experience injuries, as well as building and other properties being destroyed. So it's a very much concern when earthquake happens. Now, as the facilitator Abel said, I led the team to Achimbatepi when the structure came down under its own self-weight. It wasn't an earthquake. So we can imagine what will happen if earthquake occurs in Ghana. It will be very, very dangerous. I can only imagine the number of buildings that we can count standing rather than the collapsed ones. Because I'm very much convinced that a lot of buildings that will come down will be more than that will stand. If we are to have that magnitude which happened at Turkey. So we are very much concerned. And this is the time for our structural engineers and geotechnical engineers and the architects to sit up and make sure that we do what is right. And the existing ones, we know how we are going to retrofit it. Now, with Turkey, with high standard of knowledge in terms of design and constructions as compared to our part of the world, I think the picture that's shown, you look at how the structures were reinforced and even that it couldn't stand the earthquake. Look at what was happening at Achimbatabi, the pillar. You have a whole column and no reinforcement. A mass concrete. It's not a reinforced concrete as a column. So can you imagine what will happen in Ghana should that thing occur here? These are some of the columns that I said. And the concrete, when we measured as low as 12 Newton per millimeter square. And that was a structure which people were worshiping in. It was up to the 4th floor. So the concrete strengths were very, very, very weak. And you can see as the picture depicts. Alarming rate of building collapse under self-weight in Ghana, not to talk of earthquake. In recent times, we have airports, a building collapse, 4 people injured, cantonment, uncompleted buildings collapse, 3 people died and 18 sustained injuries. New Boy Town, it happened, 1 dead, another person collapsed, in that order. So when even 1 person died, it's a matter of concern, not to talk of 22 people who perished at Timbetebi. Now, in recent times, I think my previous colleague, Engineer Bimpom, made mention of 4 building collapse, but my search came out that we had 5. I think in early part of this year, somewhere in February, a storage building at Ashoman 1 afternoon collapsed. At Denta, we had on the 5th of March. So within March, that we had 4 being collapsed, being without earthquake. So you can just imagine what will happen with earthquakes. This is something we have to be very careful, and I will urge all the structural engineers, the geotechnical engineers, the architects to be very cautious. And as this product has come out, I believe a lot of them will enroll themselves to the training and upgrade their knowledge in design. I am not a structural engineer, so I will urge them to upgrade their knowledge with new ways of designing to resist this kind of casualties happenings. They are following our past earthquake experience and the rate at which our buildings have started collapsing under self-weight. Turkey's experience must be a red alert for our professionals moving forward. Our designs must factor in resilience against earthquake. So here, we don't have much earthquake structural designers, but now we have opportunity. Prota is giving an opportunity to those of you who are into designing to upgrade your knowledge. I think it will be a very good market as well when you get that knowledge, so that we can give technical advice or be a trainer of trainees to other engineers so that they can do what is right. Not only in designing, what about if we are installing the design, the construction? What we see, a lot of developers don't engage professionals even after it has been designed. That's what we have witnessed. When you go to the site, you see a lot of these craftsmen doing what engineer or professional supposed to do. You'll not be surprised seeing a draftsman designing up to 10 or 5 stories, which in my opinion, we are not supposed to do. White architects are there. And the structural engineers, you will see CAD technicians doing structural engineers, and they don't have the basic structural mechanics. And they still go ahead and be designing. And unfortunately for our parts, the assemblies that are supposed to see to it that the right thing and the right designs are being done before approvals are given. And you'll be surprised some of these design pass through, and beside when they start installing them or during the construction stage, they are about 13 stages by which the assembly is supposed to satisfy before the building is completed. And when even it is completed, they are supposed to issue certificates of occupancy. It is not happening. So we also urge our local government engineers and the authority to set up. Now, planning, preparing, and educating the public is very, very crucial at this stage Let's look at what happened at Turkey. They were able to mobilize enough rescue teams to rescue a lot of people, even though 50,000 people perished and 107,000 people got injured, and 11,000 cities affected, and 20,000 buildings collapsed. So this is a time I think the engineering fraternity with the NADMO, there should be a planning towards if such disaster happens, what do we do? So that people will be more educated and will be calm when it happens. And what do we do to rescue people who will be entrapped under the rebels when it happens? So education is very, very important to the general public as well. So when they are putting up structures, whom should they consult? Whom should they engage? What are the professionals they are supposed to employ in the designing stage and the installation or the construction stage? We need to intensify our education to the general public. It's very, very important. And we have enough laws by which when it is implemented, at least even when it happens, the casualty will not be so much. Where we have the Local Government Act, Engineering Council Act is in place, who to design, who to supervise. We have the building code, National Building Code, which have been revised. We have the Spatial Planning Act. They are all there, and the processes one have to go through when in designing and in installation. So we have to be up and do what is right, because we cannot wait for this to happen to us. We must learn something from what has happened at Turkey. Even though they are far advanced than us, at least we can do something. Because Ghana is not so much in the red zone. So the magnitude we don't expect is so high, but it can happen. Anything can happen. So we have to prepare and do what is right. Now, with all these things happening, I think Engineering Council in its own wisdom has constituted a committee to investigate and advise the way forward. And the outcome of the investigation should inform design professionals in future projects. So informing the design professionals, this is a point that Prota has come. So it will not be wrong if all our structural engineers have taken through this seismic retrofitting designs, at least, so that they can properly advise the general public and the government as well, because the government also in Ghana, when you talk of capital intensive projects, government is also part of it. Are they doing what is right? We can't tell. But once our engineers are there, they have to upgrade their knowledge and do what is expected of them. Turkey lesson should be a great warning to Ghanaians, engineering professionals, to avert possible time bomb awaiting to occur. We don't wish it occurring though, but we have to do what is right, especially our designers and those who are in authority to check that whatever we are constructing, whatever we are installing is approved and it meets the requirement and the stages that they have to satisfy, they have to do so. Especially to those in the local government assemblies. In our market too, as Engineer Ben said, we have a lot of inferior material in our market, and that one too is a very great challenge. Ghana Standard Authority, they recently had discussion with both Institution of Engineering and Technology and GHIE concerning the standard of our roads. Is very, very, very challenging. The quality of it and the sizes and the standards are very, very low, and they are aware of it. When you talk of the cement too, I recently saw that Ghana Standard Authority intend going around to test some of the cement products. So this tells you that we have a lot of substandard. So even if you designed and the installer is using a substandard materials, that place too, there's a challenge. So we have a lot in our hands to do in terms of education, and enforcement by the state agencies. We have a lot of, and it is a time I urge the Engineering Council to actually publish those who have been licensed, so that the general public can fall on them at their website and assist a request for their assistance when they are in need, because it's very difficult. Maybe somebody want to engage engineer and he doesn't know where to go. Even on the website, we can have an album of engineers whom they can contact. So it's a high time they publish at their website the licensed engineers, those who are structural engineers who can assist them in their design, construction engineers who can assist them in the installation, and that. Thank you. So these are the pictures of some of the structures being put up in Ghana, so you can imagine. Thank you.
Thank you so much, Engineer Henry Barton. Your presentation was, concise, and we could actually relate, and I believe everybody who was, who was looking at it is actually going to feel, could relate with it, because no earth tremor, and you're having about three buildings collapsing on their own, just by themselves, that is something that calls for a lot of concern. And Engineer Barton, we really appreciate your time, and I know everybody back there, every participant will be applauding you for your outstanding presentation, and we appreciate the insight and knowledge that you have shared with us. We are grateful, all of you. So we will end it here. We thank you all for your time. Stay blessed. We'll be meeting you subsequently for subsequent trainings. Thank you, and then please connect with us, and let me show you how you can get the software as also an asset for you. Prota is an asset. Try to get one. Thank you so much. God bless you. Stay blessed. Bye-bye.